All right. So last time we talked a lot about what binary trees and binary search trees and general trees are, and a lot of terminology. So this time we're going to try to sit down and actually write some code. So here's a little client program that I think I did last time. And so what we need to do is we need to have a constructor, we need to have print, and we need to have insert. And then we've got something we can test, right? Okay. What did I call it? Oh, wrong one. Get rid of that. Whew. Binary tree. Okay, so we're going to do private first. This should look familiar, right? I'm pretty sure we did this last time. I just don't know what happened to the file. Node star group pointer. Then public. I'm going to have my size type. Which means I'm going to have to I think I can do. Yeah, I better just play it safe. I know it. I'm pretty sure it's just a bit to me.
You don't have to include it in the client methods yet, right?
Sorry?
You don't have to include it in the client methods yet, okay? You include that upstream part.
Yeah, but I probably will anyway. Okay, and then we need a constructor, and we need print, and we need insert. How's that look? Okay. Binary tree page. Okay, and now we need a implementation file. Which we will call binary tree.cpp. Is that what we're calling it? Okay, so pound include yeah, that. And we're going to need iostream, and we're going to be using and then binary tree. So our constructor is going to do what?
Set the root pointer to null.
Yep, root pointer gets null.
You have to put this in your namespace.
Yes, I do. Yep. So name space in tree. I think I got that right. Whoa. All right. 1 out of 3 functions already done. Okay, so the way that we're going to have to do any recursive functions is we're going to have to set up an auxiliary function to do it. Okay, because the calling object in these functions that we're writing now is something of type binary tree. And as we work our way down the tree, what we're working with are not things of type binary tree, but things of type node or node pointer, right? It's just basically going to be print augs. On the node star node pointer. Oh, jeez. We're sending it root pointer. That make sense? So now root pointer is a node pointer, and so this print augs function we can call recursively on different nodes within the tree. And actually the other thing that we're going to need to do is that auxiliary function is going to need to access the data members in the private data members in our class, right? So how are we going to solve that? Make it a friend function. So friend print node. Thank you. Node star root pointer. Oh yeah, friend boy. Okay. So now we're going to have void print node star root pointer. Print augs. Okay, I'm not sure why it's saying that, but what's wrong with what I have there? I have a suspicion that maybe the reason this is has a red squiggly is because of the problem here. No clue. So does this function know about the node? Is node a global identifier? No. Node is declared inside the binary tree class, right? So this function needs to know that, right? Yep. So that got rid of that. We got another squiggly now. Is inaccessible. Let's hold on to that. maybe it just needs to have us try it to figure that out. Okay, so here's the fun part. Here's where we get through our recursion finally, right? So the recursion is, the base case is if root pointer is null, then we do nothing, right? Okay, so I'm going to flip that around the other way and say if root pointer is not equal to null, so print args and then cout root pointer arrow data, and then the right side. Okay. Now that's a good question. Is this going to print it out in any particular order?
It'll be ascending order.
It'll be ascending order. So let's. So yeah, it's first going to print this subtree, then it's going to print this, then it's going to print this subtree, right? And when it's printing this subtree, it's first going to print this, then itself, and then this, and then we're back up here. So yeah, it's going to print these in ascending order. Okay. Remember when we talked about prefix and infix and postfix? I think I drew some trees, right? Yeah. This is what kind of a traversal is this? Prefix traversal or infix traversal or postfix traversal? It's hard to say. You're processing, whatever it is we're doing, we're doing the processing in the middle. So it's an infix traversal. As a matter of fact, we're just printing, and remember I said for infix it was the second time you saw the node. If you're going around the tree, the second time you see the node is when you print it. That's an infix notation, and that's what we're doing here, right? 7, 30, 40, 50. That's a little aside. I guess I won't. I don't want to go too far down that path at this point. All right, so we can't really try anything yet because we still need to work on insert. So it's going to be the same situation. Oh, we still have this. Let me try compiling it, see what happens. Init file found before the left brace was matched. Oh. Forgot to close my namespace. Still have that node underlined. What's up with that? Okay. Yeah, still won't go away. All right. All right, so insert. We're going to need an auxiliary function just like before. And then we also need the number that we're going to be inserting. So the original function, binary tree, : insert, just takes a number and then calls insert logs with root pointer and none. Okay, so far? Just like before. And now we've got node underlined just like before. Okay, insert. What's our base case going to be?
Same thing. Root pointer is null.
If root pointer is null, that seems like that would be a base case, yeah. As a matter of fact, if you think about it, when you're building a binary tree, you're always going to be adding leaves. So you're always going to be adding something at the very bottom of your tree. So as it turns out, that is going to be the base case, right? When root pointer is null, that means that you have reached the bottom of the tree and it's time to create the node and insert it. Okay? Okay, so if node pointer, no, root pointer is null, create a new node. Root pointer. Root pointer, arrow, data, num. What else?
Left and right.
Left and right get null. Okay. Root pointer, arrow, left, it's null. Root pointer, arrow, right, it's null. Anything else? I think that's it. Okay? And then the recursive cases are actually the easy part, right? Tell me what's tight.
If num is less than root pointer arrow data, insert auxiliary left or root pointer arrow. Or less than or equal to it.
Get less than or equal to. And then insert augs.
Root pointer arrow left.
Everyone okay with that? And then same thing on the other side, right? What do you think? Starting to feel a little more natural? Good. Any questions? Yeah.
Do we need to make the, fill out the parent pointing to the child?
Okay, so that's a good question. That's the, if you start thinking about this in a lot of detail, that's where it's possible to get hung up on. And that is, so here's root pointer, but how do I know that this is connected to the parent from before? One thing is that there is actually one more thing we need to do here that we don't have quite right. Let's see if we can visualize this for a second. Okay, I'm not totally sure if I'm going to be great at articulating this, so let's see how it goes. So let's say that we are adding the number 3, okay? And so we get down to the bottom of our tree here, and this node here is actually like this, right? Oop, that's not what I meant. Ah, that's not what I meant either. Take 2. Hold on. Okay, that's how each node actually looks, right? And right now those 2 are null. Okay, so when this node, right? Okay, so when that's not what I meant. There we go. So when we're calling insert augs, and root pointer is this pointer right here. Okay, we come in here, and we're going to go to this else if, right? Num is less than or equal to the root pointer arrow data because we're trying to insert a 3. So we call insert augs, and what we send is root pointer arrow left. Okay, so we're sending null, basically, right? We're sending null, and then we come back up here. If root pointer equals null, it is. So we say so here's root pointer. Oops, try again. Here's root pointer. And we're going to say root pointer gets new node. Okay. Root pointer arrow data gets num. And then null and null. And we're done. Okay, so we actually did not succeed in attaching this up. Any ideas what the fix is here? I'll give you a hint. It's not a problem with our recursion. Our recursion is correct. Yeah.
You want to pass a reference to the pointer?
So right here when we call insert augs, the whole point of this function is that we want to change what root pointer is pointing at. Make it point to something different, right? So what we did here is we sent a copy of that pointer was just null. What we actually want to do is we want to send that memory address. Okay, so if we try that again, Now what we're doing is we're sending this memory address right here. So when I say root pointer gets new node, root pointer is just another way of saying this thing right here. And so root pointer gets, oops, new node. Okay? Any questions about that? And then, and that's, I can stop there, right? You got it. And I don't have to fill in the data and all that. Questions about how that's working? Okay. Let's see. So that means I need to change my header file. And is that it? I'm done? Ready to test this thing? Ah, thank you. Unknown identifier node. Yep. I always say binary. Okay, try again. Cool. Okay. Let's go ahead and work on find. So to find, and then let me just, so find is going to be a value returning function that returns the value that was found. So I'm going to say int value gets list.find num, and found. Then I'm going to say if found okay, else yeah, not.
You mean to be updating the variable value?
Yes. I just actually probably result would be better. How's that look? Okay, so now we just have to write a find function. This should be starting to look a little familiar. Sorry, it's cold.
It is very cold.
So void find num bool ampersand found, and then we're going to need the same old args function. This time we don't need to change it, right? We're just finding stuff. So const node star root pointer. Yeah, I know I'm not changing anything. So if I make it, if I just leave the const out, okay, this is actually, I'm glad you asked. It's kind of a subtle point. If I leave the const out, that means because it's passed by value, I can't change what root pointer is pointing at. But I could still, wait, sorry, I said that wrong. I can't make root pointer point to something different because this is passed by value. But I could change the thing the root pointer is pointing at. If I put const there, that means that I can do neither of those. Let's see, this is going to be int num bool found, right? Yeah.
Your find functions, not your find functions.
Oh yeah. Okay, so int binary 3 : find oops, return find bugs. Pointer none. Okay, so far. And then int find binary 3 node star root pointer. Man.
You need to put that auxiliary after find.
Yes, thank you. Okay. All right, so we're ready for the fun part now. Base case. Okay. If root pointer is null, what does that mean? Found is false. Well, we have to return something, right? So basically our post condition for this function would be that if it's not found, then the return value is undefined. So we can just return any integer, doesn't matter what. So return 0.
You don't need to add anything else to that statement at all. It's good enough there. Statement.
No, I'm not done yet. Right, so there's the base case. What's next? Recursion? Recursive cases? Another base case?
Root finder.
Right. So else if root pointer arrow data is num. Oh yeah. Found gets true. Return num. Actually, we should probably just be, what we're really returning is root pointer arrow data, right? And we're pretending that actually something more interesting is going on, right? Oh yeah, sorry. Actually, I guess I don't technically, but I think it works better. Okay, so I think that's it for our base cases. Now we just have the standard recursive cases, which is num less than or equal to. I guess if it was equal to, we would have already stopped. If num is less than root pointer arrow data, return oh, jeez. You guys never do stuff like that, right? What do you think? Okay. Let's try it. Const. Here I have a const. And here I don't. Does that make sense why I got that error message? It's telling me that, or it's thinking that this is, it doesn't know it's a friend function because the signatures didn't match. Okay, so there's our list, and we can just start finding the numbers. And checking to see what happens if it's not. Whoa! I hit the wrong key.
Really though?
Because it wasn't. I hit a key that wasn't a number, and so our CN went into an error state. So So 4, 5, 7, 9, 80, and 85, or 1. Okay? All right. You guys know what's next? So, remove, yeah, or delete is what I think we called it before. So, let's see.
No, I was going to say break.
Break? Okay. Let's do a little further.
That's cool. Carry on a roll, go ahead.
Okay. Actually, probably it's more like But so list dot, and I can't say delete because that's a key, a reserved word. Found, if found, the list is now, oops. List up. How does that look? Okay. Yeah.
So if I really want to delete it, like a node that has 2 children, do you have to make the right node for the parent?
Excellent question. Let's go back and take a look at our picture a little bit and figure out how this is going to work, okay? So let's start with the easiest cases, okay? If I want to delete the 7, that's easy, right? Okay, just reset this pointer to null and make sure that I call delete. Same thing with all the leaves, right? Easy to delete a leaf. Okay, let's actually, hold on a second. I can get this, as usual, my notes are all messed up. Let's consider the case this. Let's say that there's some more stuff down here just to make it a little more interesting. Okay, I don't care what those numbers are. Well, actually, let's better make sure that what we're doing actually makes sense. So 35 and 45. Okay. If I want to delete this node right here, what's the best way to do that? I can't just delete it, right? Okay, so yes. I guess at this point, though, I'm asking just what am I going to do with this picture? Just looking at, go ahead.
You're going to make the root pointer point at the 40.
I'm going to make the root pointer point at the 40.
Yeah,
and then delete it. Will that work? If I do that, will I still have a binary search tree, meeting all the requirements of a binary search tree? Yeah. So in this case, still fairly easy, right? Not too hard. What if I bring this back, though? And just for fun, I guess I should add some more down here. So this is 20, 25, 5. Okay, and I want to delete the 30. Can't just make the 50 point to the 40, right? Okay, so here's what we're going to do. This is actually fairly difficult, and I have to tell you that let's see, my senior year in college, I was applying for summer jobs, and I had an interview with HP, and one of the questions that they asked me in the interview was, how do you delete a node from the middle of a binary search tree? And I got it wrong. So make sure you get this. It's pretty hard though. So let's see if I get it right this time. So if I'm going to delete the 30 here, what I need to do is go down to the right subtree and find the largest item in the right subtree, which is always going to be just going all the way down to the right. Okay. So the 45, I take this 45, and so what I'm going to do is delete that and change this to, whoops, 45. Nope.
You have to make the 40 to 45.
Maybe it was the left subtree. Shoot. See, I was traumatized by that experience, and I still can never get it right.
I figured what you did. You said to put the 45 where the 40 is, and then move the 40.
Well, right, but then if that could work, but there's an easier way. Because if this was a long chain, then I'd have to swap all the way up. And okay, so I knew I shouldn't have gotten so excited with my big X there. This was 45. No.
I think you have to move the 35 over there.
This was, what was it, 30? It was 30. Okay. I'm just trying to set up the original situation we had. 45. Okay, so maybe what it is you have to go to the left subtree and find the largest item from the left subtree. Would that work? If I put 25 up here? That makes sense, right? Because everything in the left, if you take the biggest item from the left subtree and move it to the top, then everything in the left subtree is still going to be less than it. So take the 20, so I'm going to be deleting that and putting the 25 here. Okay? All right, so the code for that is going to be a little tricky. But let's at least get a start on it here. So delete, and this time we want it to be, that's by reference. That looks okay? All right. Thinking it's going to, wait. No. This is just going to be void. Better? Okay. Copy that whole thing because I think it's going to be pretty similar to that, at least in the basic structure. So void del oops. That look right? Okay. Void. Dogs. Okay. So if root pointer equals null, found gets false, and we're done, right? Else, let's do the equal to last, okay? Because I'm gonna, even though that's the base case, I'm gonna push it to the end because it's the most complicated part. Okay, so I'm gonna actually just take this out for now. Okay, so else if num is less than root pointer arrow data. Yeah. And then else if num is greater than root pointer arrow data. Del augs root pointer arrow right, num found. Okay. So now we've got hold on for a sec. He's got these the different steps set out in pretty pretty good detail here. Okay, so we're going to say, first of all, that we're going to take care of that simple case, which was, remember when I first put it up and I said, how do you delete this? And you said, oh, just make the root pointer point to the, what was it? Make the root pointer point to the right child. So what should the if be? If what? I can feel my brain starting to slow down. Sorry? Oh yeah, good idea. So if we say that the first example I gave you was there was nothing over here on the left.
Root pointer arrow left equals null.
If root pointer arrow left equals null. Okay, so as soon as I'm writing that, or as soon as you're writing something like that, you should be thinking, okay, wait a minute, I'm saying root pointer arrow left. Do I know for sure that root pointer isn't null? Yeah, I already checked for null. Okay. Okay, so in this case, what do we do? So first of all, forget about the memory leak problem and just tell me what to do.
Root pointer gets root pointer arrow right.
Flip pointer. Root pointer gets root pointer arrow right. That make sense? So here's, let's see, we're trying to delete this. And so this line right here is root pointer. So I'm saying make this point, instead of pointing where it's pointing now, make it point to root pointer arrow next, which is the root pointer arrow right, which is this guy. Okay? So to avoid the memory leak, though, we're going to have to do binary tree. Yeah, binary tree : node star temp pointer gets root pointer right. Okay. Okay. All right. So notice what I'm doing here. I'm postponing the pain as long as possible, right? Getting as many of the easier cases out of the way as I can. Okay. And so now we've taken care of every possible conceivable situation except where we're deleting a node that has a left subtree.
What about leaf? Is that not different?
Well, this case is actually going to cover it if it's a leaf too, right?
Oh, those are the same thing.
Yeah.
Okay.
So that's a good point, actually. So if it's a leaf or if there's no left subtree, I do the same thing. Okay. Here's what we're going to do. I'm going to postpone the pain even longer. I'm going to say, I'm going to have another delete auxiliary function, which actually, basically what that is going to do is it's going to remove the largest item from whatever the subtree is that I give it, right? So let me call that remove max. Right, because I want to remove the max from the left subtree. Say that again? Okay, so the question is, should that be a value returning function so that we know what the value is that we remove? The answer is I'm actually going to write it as a void function, but give it a second argument that's going to be a reference argument. Pointer arrow left. This is just a temporary variable, right? Max. That make sense?
Yeah.
Say again?
You have to define max somewhere, or is it just
Oh no, I do have to define max somewhere. I guess I should just do it right in there. Okay, so that function is going to remove the largest item from the left subtree, and then what I need to do is do an assignment here, right? Something. What's the assignment I want to do now?
Root pointer arrow data gets max.
Root pointer arrow data gets max. Okay, pretty good. I'm thinking maybe now would be a good time to take a break. I actually didn't mean to go that long, but we'll take a break, and then we'll come back and do the remove max function. Okay, so sorry? Oh, thank you. What we have left to do is just write the remove max function. So I put it here in my header file. And so let's see what we can do here. We're going to have void remove max binary tree : node %root pointer int %max. Okay, so how's that going to look? So right now, in our example that we're working on, root pointer is this pointer to the 25, right? And we are going to try to find the largest number in the left subtree. So is that going to be a recursive function or not? Yeah, because we're going to basically go down the tree until we get to null, right? Okay, so that means we get to start thinking about the base case. What's the base case going to be? Well, if we keep going, so we're going to actually, okay, hold on. When we called remove max, sorry, I got confused there for a second. When we called remove max, we sent it this pointer, right? So actually, in our remove max function, this pointer here is the root pointer. Okay. How will I know if? So the base case is when root pointer is pointing at the largest item, right? How do I know if root pointer is pointing at the largest item? Root pointer arrow right is null. How does that sound? Well, it means it means there's nothing in the right subtree, which means there can't be anything larger than that node, right? So that's correct. If root pointer arrow right is equal to null, that's our base case. And so what we want to do is set max equal to root pointer arrow data. Everyone with me on that? Okay, so in this particular case, this won't happen the first time. This will happen when root pointer is this arrow here pointing to the whatever that is. 25. Oh yeah, and this is that was 30. Let me just set that up so I don't confuse myself. Okay, so that's 25, even though you can't see it. So this pointer to the 25 is the root pointer at this point in our recursion. So we just need to say max gets root pointer arrow data. Anything else? we actually have to delete root pointer. Okay. Hold on. Yeah.
We need to check if there's a left subtree though too, right? So we don't have balance.
Right. So so if this node here has a left subtree, thank you. That's what I was. So let's say that this is actually pointing to a node here, or an entire subtree. We can't just delete this, right? What do we have to do? We need to make this is root pointer, right? The thing pointing at the 25 was the root pointer. Okay. We need to make that pointer point at this left subtree. Okay, so just forgetting about the memory leak for a second, what we want to do here is root pointer gets root pointer arrow left. Okay? That doesn't make sense. Sit and think about it until it does. This pointer right here, we're getting rid of this node, the 25, because it doesn't have a right subtree. Okay? But it does have a left subtree. Every item in this left subtree has got to be bigger than 20. So we're going to make this subtree down here be the right subtree of 20. And that's what this statement over here does. Okay? Now we need to deal with the memory leak situation. So it's going to be the usual thing where we have to get a temp pointer. Okay, that's our base case. Our recursive case. If root pointer does have a right subtree, what do we want to do? Remove the max from that right subtree. What do you think? Oh, that's not the first time I've done that today. How's that look? Better? Let's try it. Ooh. Don't look at that. Pay no attention to the code behind the curtain. Let's try it. So there's our list. 3, 5, 6, 7, 9, 17. Okay. Not worried about find right now. We want to try delete. So an interesting exercise would be to actually build this tree and see what it looks like. Right? Because those 6 numbers could be placed in the binary tree. The binary tree, there's a lot of different ways the binary tree could look that would hold those, right? Depending on which order we put them in. And when I'm testing my delete function, I probably want to check, I want to make sure that I'm testing different situations, like deleting a leaf, deleting a node with no left subtree, deleting a node from the middle. So we're not going to do that much detail right now. So the 3 was the first thing that was, no, the 5 was the first thing that was put in. So I know the 5 is going to be the root, right? And then 9 is going to go on 5's right. 3 is going to go on 5's left. Actually, that might be kind of interesting. Give me just, see if I can do this in 1 minute. So 5 goes in first. Then 9 goes in, so it's going to go over here. Then 3 goes in, so it's going here. Then 7 goes in, that's going to go here, right? Bigger than 5, smaller than 9. And then 17 is going to go here. And then 6 is going to go to the left of the 7. So none of this is down here, right? I really do need to figure out how to erase it.
You can just grab a piece of the white and then just drag it over.
Grab a piece of the white. All right, I'll work on that next time. Okay, so that's all gone. But 7 has a left subtree of 6. Okay, so not a very well balanced tree. Well, not unusual for a tree to be a little out of balance like this. Okay, so now I'm thinking about what order I should test these in. Let's if I delete the 5, what's going to happen is the 7. If I delete the 5, what I put up here in its place is the largest item from its left subtree, so it's going to be the 3 up there. Sure, let's try that. Actually, no, let's delete a leaf first. Let's delete the 6. Okay, that was easy. The 6 is gone. And then, is there something that doesn't have a left subtree but does have a right subtree? There's not. Oh well. Let me just delete the 5 now. All right, so now I've got whoops, 3 there. And that's gone. And that's gone. Now do I have something that has a right subtree but not a left subtree. So let me try the 3 next. 7, 9, 17. So that just means that we got rid of this, and this is the new root pointer. So then I'll just do 9, 7, 17. Okay? And then if it's not found, it says not found. Okay, one more thing real quick. Actually, I still have 5 minutes. The other thing that I was thinking about is that really here, these friend functions should be private, yeah? Because they're not for the client programmer to use. So did I just do that one? Dialogues. No, that was dialogues. Oh, something went wrong. Oh, there we go. 2 more. And we should probably just make sure that it still compiles. Uh-oh. What do I do? Sorry?
Yeah, we should check.
Oh. I think that was it. There we go. All right. I will see you on Wednesday.